Dear students, in this section we are going to discuss the concept of magnetic field due to circulating charge. Let us consider a point charge rotating in a circular path of radius small r. You can observe here this point charge having magnitude small q is rotating in this circular path of radius small r with a constant angular velocity omega, right? Suppose if you focus at this point, suppose you consider certain imaginary section in the path of rotation, you will find this point charge will repeat or again and again cross that section, and we define current is rate of flow of the charge. So if we calculate the rate of flow of the charge through any of the section of the circle, we can find the equivalent current due to rotation of the charge. So let us calculate the equivalent current due to rotation of the charge. Here we can write equivalent current as charge, this is a small q, divided by time period of rotation, that is q divided by capital T. And capital T is the time period of rotation, and 1 upon capital T can be written as frequency. So here we can write I equal to small f multiplied by q. Small f is the frequency of rotation, and we know omega, that is the angular velocity, is equal to 2 pi f. That means f, that is the frequency, should be equal to omega divided by 2 pi. So this expression can be written as omega divided by 2 pi multiplied by small q. So this is the equivalent current that is developed due to rotation of this charge. Now we have the simple formula for finding the magnetic field at the center of the circular loop. We have the formula B equal to mu naught I divided by 2r, right? I is the current in that loop and r is the radius of the loop, and here the equivalent current is equal to omega divided by 2 pi multiplied by q, and radius is given as small r. So here we can write B equal to mu naught, and in place of I we will write omega divided by 2 pi multiplied by q divided by 2r. Now we can rearrange this expression, and this is the final expression for the magnetic field at the center of rotating due to rotation of this charge, that is mu naught q omega divided by 4 pi small r. Now one question arises, if instead a point charge, if a ring having charge small q rotate in the same style, that is the same angular velocity, and ring is having the same radius small r, in that case also we will get the same result, because the charge crossing in any section, if we consider any section here, now you consider this as a ring and you consider any section, you can follow the tip of my pen and you will find in this time interval same amount of the charge will pass through that section. That means the equivalent current in case of the circular ring will be the same. That means we will get the same result as the point charge. Now let us discuss one important thing. If the ring is rotating and if we are interested to find the magnetic field at the axial position of the rotating ring. Now consider this ring. You can observe here the ring here is having radius capital R, and charge per unit length is lambda, and charge is uniformly distributed on the ring. Suppose this is the non-conducting ring where charge is uniformly distributed, right? This is a thin ring and it is rotating with the angular velocity omega. And here we are interested to calculate the magnetic field at point P at a distance x from the center of this ring. Okay. Now we can say this rotating ring is equivalent to a current carrying loop, and we can find the equivalent current by considering any section here. Suppose you are consider section here, you can follow the tip of my pen. You will find the total charge of the ring will repeat after time interval capital T. Capital T is the time period. So here we can find the equivalent current as Q, that is the total charge on the ring divided by time period. 1 upon capital T is small f, that is the frequency. So we can write I equal to f multiplied by q, and f is the frequency which can be related with the angular frequency. Angular frequency omega can be written as 2 pi f. So F equal to omega divided by 2 pi. So this is the equivalent current, right? Now we are given the charge density lambda, and you know the length of this wire is equal to 2 pi r. That means the total charge on the ring in terms of the charge density should be equal to 2 pi r multiplied by charge density, that is lambda. Okay, and now we can substitute this charge value in this expression. So I is equal to omega divided by 2 pi multiplied by 2 pi r multiplied by lambda, right? So this is the current, equivalent current. Here you can observe 2 pi and 2 pi will get cancelled. So equivalent current for this loop should be equal to omega r multiplied by lambda. Now we have the formula, that is the ready-made formula for calculating the magnetic field at point P. You know the formula, that is mu naught I r square divided by 2 r square plus x square to the power 3 by 2, right? Now we know the value of I. I is equal to omega r lambda. So let us substitute this value. This is the value of I, right? Now this is the magnetic field at this point P. You can find the magnetic field relation at the center of this ring by substituting x equal to 0. Suppose you are interested to a magnetic field at the ring of the rotating loop, right? So put x equal to 0 in this relation. So after placing x equal to 0, we will get the magnetic field at the center of this rotating loop in term of lambda, right? We have discussed the magnetic field if charge is given, that was having this value, right? And if charge density is given, so we get this relation mu naught omega lambda divided by 2. Now let us move to one illustration. The illustration is a non-conducting thin spherical cell of radius capital R has uniform surface charge density sigma. The cell rotates about a diameter with a constant angular velocity omega. Okay. Next part of the question, it is asked to find the magnetic induction, magnetic field B at the center of the cell. Okay. We know when cell rotate, current is induced due to the rotation of the charge, and we can consider this rotating charge as individual rings rotating about the common axis. Common axis is nothing but diameter of the ring, right? So here we can consider the rotating cell is a collection of the many rings rotating about the common axis, and that is the diameter. So let us consider this is a spherical cell, and let us take one sample ring, elemental ring at the surface. This is the ring. Okay. Let us define the angular position of this ring. Center is here. So join center to this ring. This angle is theta. Okay. And angular width of this ring is equal to, consider this angle, this is d theta. Now this distance, that is the width of the ring, that should be equal to, radius is r and this angle is a small angle d theta. So this distance should be equal to r d theta. Okay. Now it is required to find the charge of this ring, because this ring is rotating and this ring is equivalent to a rotating loop. So it is requirement to find the charge of this ring. For calculating charge of this ring, we should calculate the area of this ring. If we open this ring, the ring will become rectangle. So suppose if we open this ring like this, this will be rectangular strip, you can observe, and the length of this rectangular strip should be equal to 2 pi multiplied by this radius, suppose small r, 2 pi small r. Okay. And here this thickness is r d theta. Okay. This is r d theta. So we can write 2 pi r, this area of this ring should be equal to 2 pi r multiplied by capital R d theta. Small r is this one. This is capital R That means small r should be equal to capital R multiplied by sin theta. So let us write the area of this elemental ring dA. This value is r sin theta, right, as we discussed, and the distance of this center of this elemental ring from center of the sphere, you can observe this is the center of the sphere, this distance is r cos theta. So let us now write area of this ring. This is equal to, as we discussed, 2 pi small r multiplied by r d theta. Small r equal to capital R sin theta. So let us substitute this value. So this value is 2 pi r square sin theta d theta, right. Now charge is uniformly distributed on the surface. That means the charge on this ring should be equal to charge density, that is sigma, it is given as sigma, multiplied by area of this ring, that is 2 pi r square sin theta d theta. So dq can be written as, this is sigma multiplied by dA, and this is equal to sigma 2 pi r square sin theta d theta. Okay. So this is the value of the charge on this elemental ring. Now we can find the equivalent current corresponding to this rotating loop. This should be equal to I, this is the current in this loop, I equal to frequency multiplied by charge. Okay. And frequency is omega divided by 2 pi, because omega equal to 2 pi f. So we can write here, right, let us write the charge value which we have calculated. So angular frequency is omega, that is frequency. So here we can write current corresponding to this loop is equal to omega divided by 2 pi multiplied by dq. Okay. Now we can substitute the value of dq we have calculated. This one, this is the current corresponding to this loop. Okay. Now we can consider a number of the rings are placed on this common axis, common diameter you can say, and if we want to calculate the magnetic field due to this rotating loop, we can consider the magnetic field at this point as a magnetic field due to this ring at the axial position. So we can use the formula for the axial position of the ring, that is dq equal to mu naught I r square, r is the radius, divided by 2 small r square plus x square. Small r is this one, x is this one. So we are using this formula, right. I we have calculated, small r is equal to capital R sin theta and x equal to capital R cos theta. So let us write this expression for the magnetic field because of this rotating loop at this center. So this is the expression we have calculated up to now, this one, right. Now let us substitute the corresponding value. I we have calculated this one. So this is the dB. dB is the magnetic field due to this elemental loop which is rotating with the angular velocity omega. Now we can simplify this relation. If we take r square as common, this should be equal to r cube, and in bracket term will be sin square theta plus cos square theta, that is equal to 1, and 1 to the power 3 by 2 is again 1, and in the numerator you can observe this is sin theta and this is sin square theta. So after calculation finally we will get 1 by 2 mu naught sigma omega r sin cube theta d theta, right. If we want to calculate the magnetic field due to the complete structure, we need to integrate this term, and limit of integration should be equal to from 0, because the first ring, very first ring will be at angle theta equal to 0 and last ring will be equal to theta equal to pi. So for calculating magnetic field, we should place the limit 0 to pi and integration of this term. Okay. Now we can observe this term is a constant term and integral is 0 to pi sin cube theta d theta. That means we need to find the integration of this term. So let us write the final term in the next page, right. This was the relation. Okay. Now we can write this sin cube theta as multiplication of sin square theta multiplied by sin theta. right? And this sine square theta can be written as 1 minus cos square theta. So this relation should be equal to 1 by 2 mu naught sigma omega r integral 0 to pi 1 minus cos square theta multiplied by sine theta. Okay, and here this is the expression. Now we need to calculate this value. So here we can use the method of substitution, and using the method of substitution we can take this cos theta equal to t. If we place cos theta equal to t, and this differentiation of the cos theta will be equal to sin theta d theta, that should be equal to minus dt, because differentiation of cos theta equal to minus sin theta. So here we can write this differentiation minus sin theta d theta equal to dt, or we can rearrange this term, we can write sin theta d theta equal to minus dt. So we got this relation, substitution for this relation, and substitution for this is t. Now let us substitute the limits also. If theta equal to 0, cos theta equal to 1, that means t equal to 1. Lower limit is t equal to 1. Now if we place theta equal to pi here, this cos pi equal to minus 1, that means t equal to minus 1. That means the limit of integration after substitution should be from 1 to minus 1, and integral will be 1 to minus 1, and here will be 1 minus t square, and this is minus dt, like this, right? Now we can rearrange this relation. If we multiply with this minus, this will be equal to t square minus 1, and after integration finally, now you can substitute the limits. Okay, and after calculation we will get the final term 1 by 2 mu naught sigma omega pi 4 by 3, and if we final simplify, this is 2 by 3 mu naught sigma omega r. This is the magnetic field due to rotation of this thin spherical cell.